back in Gen Chem 1, we've learned it as something where we had a table to memorize, and it was sort of like either this salt was soluble or is insoluble. Now we're going to approach solubility in a more realistic fashion, where it's a gradient. We're going to have items that are going to be either more soluble or less soluble than some other salts, right? And to look at this, we're going to be, once again, using the idea of an equilibrium to figure out whether or not a salt will be more or less soluble. So first, let's go back to something familiar. Consider the following reaction, which is the Haber process, right? We have N2 plus 3H2 goes to NH2, NH3. So if I told you to write a Ksp expression for this reaction, that would be simple enough, right? We would first put products over reactants, and so it would be NH3 squared, and then on the bottom it would be N2 and H2 to the power 3, right? Simple enough. So some rules that you may have forgotten because it's pretty much a known practice by now is that we have to put the coefficients, right? And we can't include solids and liquids in the equilibrium expression. And that's because as you change the temperature and the equilibrium, they're not going to change along with it. So now let's approach this with something new. Let's consider that we have an ionic compound that we would have previously considered to be insoluble. So right now I have lead iodide. Before, if you looked at any of the solubility tables, we would have seen that lead iodide is an insoluble salt. So we don't expect it to dissociate in water. And instead it would just stay as solid. And this is true, but in reality, there are some times where it can't be soluble. So let's consider if it could be soluble, right? Just like any normal salt. NaCl, let's consider it like that. So if we have PbI2 and dissociates as two ions, we have Pb2 plus and 2I minus, right? And now I told you to write me a K expression, right? So the way we would do it is, we would approach it like K equals products. So our products are going to be Pb2 plus and I. And we're going to square this value because there's a coefficient of 2 in front of it, right? And now for our reactants, I see that PbI2 is a solid because that's how we started it off. It was going to be a solid initially. So in that case, we're not going to consider it for our K expression. So this is what we're left with. And this is what we call a solubility equilibrium expression. So, otherwise known as Ksp, this is defined as the solubility equilibrium for a solid and species in solution. The larger the Ksp, the more soluble the solid is. And that sort of makes sense, right? Because a larger Ksp means that we're going to have more products, or it's driven more towards the right. So in the previous case, the reaction to the right meant towards the ions, meaning it's more soluble, right? And so now there are two other instances with solubility. We can have molar solubility, which tells us the number of moles of solute that can be dissolved in 1 liter of saturated solution. Remember that saturated means that you've put the total number of molecules in a solution that could possibly be dissolved. One more after and it would precipitate out. And solubility just by itself is defined as the number of grams of solute in 1 liter of saturated solution. And so if we look over here to this table of Ksp values, you'll see that a lot of them are really small. And so this holds with the notion that a lot of these salts are going to be relatively insoluble, but in small enough concentrations, you can get them to you can get them to dissolve out in water. So let's explore this idea with a practice question. So I have write the Ksp expression for AgCl and figure out the Ksp if the molar solubility is 1.34 times 10 to the negative 5, right? So first, I've already written out AgCl into its two forms, Ag plus and Cl minus. So now, because this is a K expression, we're just going to do it like how we would normally do it. We're going to start off with the nice table, right? So we're bringing those back once again. So what's going to happen is we have our ice table, ICE. So one other thing is you might see this line I put through HCl, right? Did this because it's a solid, therefore we don't need to consider it in our changes or in equilibrium. So that's why we could just put a line through it. So initially we have 0 silver and 0 chloride, right? Because the problem doesn't tell us otherwise. Now for the change, I see that they both have a factor of 1, and because there's 0, there has to be something added to it. So we're going to say this is going to be plus x, right? And so at equilibrium, all we're left with is x. So now we go down here, what we see is that Ksp is going to be equal to products, which is going to be silver ion and chloride ion. And so we've just figured out that both of those values are going to be x, so we're going to say Ksp is equal to x squared. Now you might be asking, well, where can we figure out this x? X is actually going to be equal to the molar solubility. Now this makes sense because what we're saying is that X is the ions that are going to come when we put like a block of this silver chloride in water. But what happens is the molar solubility is how much can actually be dissolved. So from that block, only X amount can be dissolved. That's why we can say X and molar solubility are interchangeable. And so when you substitute this value of 1.34 times 10 to the negative 5 into x squared, we're going to get Ksp equals 1.8 times 10 to the negative 5. And now to find gram solubility, that's simpler enough. So we start off with 1.34 times 10 to the negative 5. So we see over here that's going to be moles over liters. And so just multiplying by the molar mass of silver chloride, we're going to get a gram solubility of 0.0019 grams over liters. And this is telling us how much we can add in 1 liter of solution to be dissolved. Now let's do a little bit more complex problem. So the questions ask, which salt's going to be more soluble, lead iodide or strontium sulfate? So by looking at the Ksps, you might be considering that strontium sulfate is going to be more soluble because it has a higher Ksp. But the problem is that both of these salts don't have the same number of ions. So we have to approach it differently. So we have our two reactions written out here, PbI2 and strontium sulfate. I'm going to do the same thing we did. We wrote out an ice table. So we crossed each of those out because they're salts, and now we're left with plus x plus 2x because there's a coefficient of 2 plus x. Now we're going to write our Ksps. So here we see Ksp is equal to x times 2x squared, right? And we're going to put this squared because, once again, it's a coefficient of 2. And over here, it's x squared, simple enough. So this one is going to be equal to 4x cubed, right? And so after I solve for x using the Ksp value given, we see that x for lead iodide is 0.0015. And when I solve this using this Ksp value, we see that x is equal to 0.005. Now, if you remember back to what we just said, we said that x is going to be equal to the molar solubility, right? How many moles can we actually dissolve? So, if you have an x value or a molar solubility greater on this side, that would mean that this salt right here is going to be more soluble than over here. So, because the molar solubility is greater, we can say that lead iodide is going to be more soluble than strontium sulfate. And so this is important to keep in mind because there's going to be problems like this in the future. And it's important that you can't directly look at the Ksps. You could do this if the ions are the same, but I always err on the side of caution, and I would just figure out comparing the molar solubility because that's true for all salts. And so that's going to be it for this video. In the future, we're going to be looking at other instances where we're going to have common ions, or what happens when you want to figure out how much it takes to precipitate out a salt.